Okay, so next talk is by Nicholas Kantas, from Imperial College.
So many thanks for the invitation and organizing this workshop and the whole program. First, just to mention my collaborators. So this is joint work with Hamza Rukwat, Ahmad El Rai, AJ Jazra from KAUST, Alex Besko from UCL, and Dan Cresson from most of you know from Imperial. Right, and we are all into particle filtering. And most of this talk will be on particle filtering. So I know it's the last talk of the session in the day, so hope you can bear with me for a few minutes. Right, so I will talk a little bit about what your community or most people here talk as data assimilation. We often also call it as filtering. And essentially we take this view that we want to approximate conditional distributions. So following the previous discussion, somehow if you're interested on certain quantities that we will call X, and I will use, if you want, these subscripts here to denote discrete time, so all the talk will be on discrete time, and little n will denote time, and somehow we have some quantities like pressure on different grid points, salinity, wind velocity, whatever, and want the conditional distribution given a lot of observations that are high dimensional maybe, but also all of them somehow here are stacked also in time. So this MATLAB notation, if you want, 0:n means all the sequence of observation from time 0 to time n. All right, we want to approximate conditional distribution. So there are a lot of approaches here, some parametric approximations like all the Kalman type ideas somehow try to propagate Gaussians. There are also ensembles, otherwise called particles, and somehow there is room, I think, to combine these methods or to use them in different ways together. And our point of view comes from what we call prescriptive methods. So somehow we want our methodology to be complemented with some useful theoretical results, right? So this is why we're really into particle filtering and trying quite hard to, if you want, scale particle filters. Maybe not at the problems right now that Gary was mentioned just before, but to go further and further and further until we reach somewhere close to that. All right, and somehow there's a short summary here of some of the challenges, right? And I'll relate to these points later in pictures or what follows. So high dimensions also mean that there's very high information content in the observation. Somehow when you project for a very high dimensional space to a much lower one, right? Somehow you're kind of pinpointing a lot, and it's very difficult to sample from the outcomes you're kind of, if you want, getting in your observations. At the same time, you have these x's to be highly correlated, both the coordinates of each xn and also between them in time, right? Usually these are some kind of Markov processes, right? So, and there have been a lot of work, and I'm thinking here in terms of particle filtering because it's my immediate interest, but a lot of these ideas appear also in different methods or other hybrids. So somehow nudging, better importance proposals, tempering ideas that we'll talk a lot about, model reductions, localizations, and we have some new idea that's very relevant to particle filtering and think is useful is to use fixed lag approximations. To be honest, the idea is not new. It's maybe 20, 25 years old and was used in the context of smoothing, but now we're trying to reuse it for high dimensions, and in the language people have seen is somehow thinking of it as localizing in time as well, in some sense, right? So here's the outline of the talk. I know a lot of you might not be familiar with what I'm talking about and need to set my notation and the problem, so I'll just talk a little bit of hidden Markov models, filtering and smoothing. These are fairly introductory pedagogic stuff. And then I'll talk about particle filtering, a very naive approach that is very basic and has no hope to work in kind of data simulation applications, and then some kind of improved approach that uses tempering and MCMC, and then talk a little bit about fixed lag approximations and how they're useful, and then just discuss a little bit and show some numerical results, right? So here's a picture of a hidden Markov model, all right? So what we have here, we have a sequence of x's, right? And remember, subscripts denote discrete time. So this, if you want the white sequence here, are some hidden states. So your ocean velocity at different times, right, at all grid points. And somehow this is a Markov chain by its own right. And let's suppose it has some transition density that I'll call F. And what we have access is to observations that basically are conditionally independent. So Y2, given all the variables here, depends on X2 and has a conditional likelihood that I will call G. All right, so this, if you want, a diagram that shows conditional dependence. All right, so you have all the Y's here, and what you would be interested is to infer the distribution of Xt given all these Y's in here. All right, so this is the filtering problem in some words. All right, and here's, if you want a picture that's a little bit more relevant, is now that I see it's a little bit more uglier than what I hoped, but anyway, never mind. So somehow, in the context of the grids we were talking just before, it could be that you have a lot of X's in one time, and you either observe some of them or some combination of them, and you get these green points that are stacked in your Y's. So moving from this grid to this grid would somehow be defined by your transition density, and this could be, for example, some stochastic PD or some PDE, and then some additive noise. And then for each grid, you will generate some observations, right? And this is a simple scheme, but you could have some more elaborate versions. All right, so now coming back to filtering, right? So what I've been talking about, the conditional distribution of Xn given all the data up to time n, is what I will call this little pi here with this, if you want, subscript with the parenthesis n, right? And somehow there's a very nice recursive formula, and this is what you would call a forecast. Somehow you're just projecting, if you want, with Chapman-Kolmogorov, the previous filter, with the transition density, and then using Bayes' rule to get the update, or what you call the analysis, right? Now, at the same time, there is an object that this guy here is a marginal of it, and this is what people call sometimes the smoothing density, and it's also important. And it's basically the conditional distribution of all the path of the states given all the observations, right? And this one has a nicer, if you want, Bayes formula, because somehow you can write the joint density of all the variables and divide by the marginal likelihood that acts as a normalizing constant. And so I'll talk a little bit about why smoothing is important. And first I will present a very basic particle filter, right? So in short, there are three steps. One is the sampling step, an important sampling step, and the resampling step, right? So you don't necessarily need to sample from the dynamics of your problem. You can do better, actually, right? And this is if you want the importance weight. And then what you're doing here is resampling, which somehow what this does is, given all these normalized values, it kind of almost, if you want, samples with replacement to basically eliminate particles with low weights and keeps the one with high weights. All right, now, notice here a few things. What I'm writing here is somehow I'm keeping the whole time dependence on the particle. So when I sample here, and this is how the algorithm is defined, you sample the whole trajectory. Often people in data simulation don't care about the whole trajectory, they just care about the last n, so they discard the rest, and that's fine. But somehow on how this is defined, because this importance weight somehow is defined on a growing state space. So I think I've missed one slide. So if you look at the sequence of these pi n's, at n plus 1, you have one extra state, right? So there's a growing state space, and somehow your importance sampling at every time acts at the level of the smoothing density, not the filter itself. All right, and this is a little bit important also on how the algorithm works and various properties that you see. And in this context, the algorithms operate on the path space, and all these, if you want, filters, and often the distribution of not only the last point, but maybe the second to last as well, and the third to last, and L to last sequence are kind of byproducts, right? Now, a lot of you have heard that particle filters don't work in high dimensions, which is partly true, especially for these algorithms, it is true, right? And what this means essentially is that the computational efficiency that you have, the number of particles you would need, would be very large because of the structure of the problem. All right, and there are two issues here. One that most of you have seen, which is weight degeneracy. Essentially what happens is, because the space is large, and it could be the observations are informative, essentially, if you don't have a good Q, let's say you use your dynamics, you will end up in places that are not representative conditional distribution you're trying to approximate, and you get very low values of the weights. But once they're normalized, one weight or a few weights might become quite large. These samples will propagate and appear as strong, but it's meaningless. All right, and somehow the variance of the weights here is important, and somehow we need to find ways to stabilize this variance as the dimension of the state space grows. Right? At the same time, there's something else called path degeneracy. And I'll just show it in terms of a picture of a toy model here. Now, if you look at the output of this algorithm, right, at let's say time 10, the blue lines here are basically the points I've propagated at any time. So you see there's a random grid that is generated at every time. These are my little, if you want, zeros here or balls here or whatever you want to call them. This red thing is the weighting function. Right, so it could have, if you use the dynamics for your importance density, it could be, if you want, the likelihood function. And some of these black lines are the output of the particle filter. So notice that if I'm looking at the final marginal, so the filter like xn given all the data, this distribution here, I have a lot of particles and I'm doing all right. But if you look at the smoothing density, at time 10, if you want the probability of x0 and x1 given all the data up to time 10, is represented only by 2 particles instead. And this is a common issue, it's a very well-known issue of particle filters. And this is because you're using successive resampling steps, and the successive selection somehow prunes the population backwards in time, and this has no chance ever to be reintroduced, right? Okay, so there are some remedies, right? And I'll try to be quick. When it comes to stabilizing the weights, right? Somehow, most people said, look, going from pi n to pi n plus 1 or pi n minus 1 to pi n in one step is hopeless. We need to break the problem down. And if you want, do more steps and somehow do more filtering steps in between that are artificial, right? Or maybe not so artificial sometimes. And then somehow control the weights at the subsequence that is between pi n minus 1 and pi n, that is your kind of design element. All right, and one approach is tempering. Essentially what you have to do is, remember you're taking the samples from pi n minus 1, propagating them with this Q importance density here, and somehow we want to go from this guy to pi n. All right, so what you do is you kind of take the weight you had before, add the temperature parameter, inverse temperature between 0 and 1, and somehow you let this define a subsequence. Change your weight so that if you want, you take like a picky function and diffuse it. This is what you're doing, so that they're stable with the dimension, and somehow do more steps. All right, so there's a problem now. This is artificial, so these are my dynamics, right? So this is what I substitute instead of F, but F and Q are some time dynamics. If I do tempering or any other intermediate distribution, I don't have this and I need to add some noise. So somehow when you do filtering and particle filtering, it's important that there is noise in how you move the particle population. And somehow one remedy is to actually use, if you want, Markov chain Monte Carlo kernels. So a very small number of MCMC moves that are invariant to this pi NL, if you want, density. All right, and this is an algorithm that has been applied in many contexts. I'm listing a few applications, so of a lot of different actually structures. Some, are standard inverse problems for PDEs and Bayes methods. Some are filtering problems with stochastic PDEs. Some are completely, if you want, on discrete spaces that are very large. And one thing to say here is that actually you can tune adaptively the temperatures in this sequence. So if you had to tune this manually, well, good luck. But somehow this is not something I would like to do. Somehow there's a very easy way to kind of decide the algorithm itself what the next temperature should be based on the quality of your population and how hard the problem is. All right, and here I'm using what ESS means effective sample size, but essentially what you're doing is the weight function is a function, and this is a simple equation that you need to solve for phi every time. So you can use a bisection method or something that is very quick. All right, so at every time, when you're at NL, you can choose the next temperature at +1. All right, once you've finished. Okay, so it's an interesting algorithm because at every time step, you kind of decide how much you need to work to assimilate, if you want, a new group of observations. This is an adaptive particle filter. It's almost the same algorithm. I've just moved the sampling step in the end here because it's a little bit more convenient. But once you decide on if you want the new temperature, somehow you compute the weights, and remember here I had a Dirac, now I have this MCMC kernel, so you kind of resample, and then you can move according to an MCMC kernel that will give you some dynamics so that you can sustain the tempering procedure and add noise to the population and maintain some diversity. All right, then somehow there is some theory on this, right? Alex, Dan, and AJ, I think for static problems, right? So somehow here, let's think that you just do it once from n-1 and n, have some interesting results, and also I think Nikolaus Schweitzer had some results around the same time that were similar with different tools. Somehow, for target distributions that are basically spatially independent, they show that you need a linear number of tempering steps to have stable weights, right? So somehow, and if you want at each coordinate separately. Schweitzer results actually did at the same time, but it's not so important. The point is here is that for, let's say, a linear number of tempering steps in the dimension, you can get an algorithm that for one update is stable and has stable weights. And if you want, provably stable with as the dimensions go to infinity. All right, now, if we ignore the dimensionality aspects, there are a lot of questions from specialists about whether my adaptation ideas, which are not mine actually, but with these adaptations ideas are convergent, and somehow there are some results. Somehow what this procedure does, that you pick the temperature, it tracks a deterministic algorithm asymptotically that has an ideal, if you want, sequence of temperatures. And if you look at the central limit theorem of both approaches, it turns out that it's the same. So essentially the adaptive version and an ideal, if you want, deterministic particle filter have the same CLT variance, right? And the only loss with the adaptive algorithm, I think, for people who like these things, is that in most particle filters you can prove a strong law of large numbers. For the adaptive ones, we've tried very hard, but somehow we ended up only with a weak law of large numbers. So there's a small loss there, but to an extent we can live with it, right? All right, so there are some issues, all right? And the analysis of Alex, Dan, and AJ was very nice, but somehow it relies on some assumptions that somehow you need some very good mixing properties for the MCMC kernel, all right? Which means that as you move in time here in this, and they placed it for a static problem. So when you move in a dynamic problem like filtering, it means that at each time step, you need to find MCMC kernels that have very good mixing quantities. In practice, this would mean that you would need to update the whole path between 0 and n of the states, which is computationally very demanding and also not online, right? Because your computation will grow superlinearly with time. So, what do I do?
Don't follow that.
Don't follow, yeah, don't worry, it's okay, thanks. So, all right, so this is one thing, and in practice, we've used this algorithm for, if you want, problems, stochastic PDEs that are high dimensional, and just updated xn in our MCMC algorithm, or something that looks like xn, but you could go on and look at this at n-1. So this is one thing. How can we find a way that we use MCMC steps that somehow might not have the ideal, if you want, properties for this in a dynamic context? And the other thing that I think is something that worries mostly, I think, particle filtering specialists is as you increase the number of tempering steps, you are prone in path degeneracy, right? So if at any time you wish to do something with xn minus 1, and you've moved these steps to go to xn, and d is large, somehow you might have a good approximation for xn, but your approximation for xn minus 1 might not be very good, right? And this is something that needs a little bit of thinking on how it will affect also some of the results that I've just mentioned, especially here. All right, so we have one idea that is borrowed from Kitagawa and Sato, which somehow the path degeneracy problem is very old, and one of the first approaches was to actually stop resampling the whole path of the x's. So if I go very quickly here, right, and sorry for the flipping, somehow they said, why should I resample the whole path? I will just resample n, n minus 1, n minus up to n minus l. And the rest of the paths I leave as fixed so that I have more diversity. And this will introduce a bias, right? And I know this is a very obscure way to write these recursions, but somehow there is a point to it. So what I'm writing here is somehow I'm writing a very, if you want, strange and funny way to propagate pi n as a function of pi n minus L instead of pi n minus 1, which is the usual, if you want, case here. And somehow here there should be a proportionality statement, but anyway, never mind. So there's a typo here, this should be prop 2. But one point that you could think is to mimic this idea, what about if this, if you want, transition density that takes me to xn minus L to xn minus L plus 1, I substituted with something else to force independence between, if you want, the recent states, xn, xn minus 1, xn minus 2, and all the ones before. So the point would be to break the correlation in time. And you could decide L according to your computational budget and somehow maybe some other considerations, right? All right, so this is what I'm going to do here. So this is why I wrote this in a way that looks a bit funny. So I'll take this guy and substitute it with mu n minus L. Now this is an ad hoc substitution that I do and change the problem. So I change the filtering problem, and now I will have a sequence of pi hat n's to track that basically forces some independence at n minus L, and also there's this alpha term here that tracks all these, if you want, steps I did in the previous time step. So here, if you remember, I had this prop 2 term that tracked how this guy is propagated. I have this alpha term that also tracks the previous mu NLs. All right, now, one point to make here is that if I do this step, and in here, I put the correct predictor, that is, if you want a filter, right, that somehow is propagated to the transition density and then you marginalize that the previous step, then at least at the level of the marginal, this step will be correct. All right, so if I put the code, if I put some, if you want, good choice here, at least at the level of the little pi subscript n, I will still be correct. All right, but of course, this you don't have and you need to somehow approximate, right? So this is the idea, and you need an approximation for this that is somehow stable with the dimensions, and somehow the hope is that we can use other ideas like other ensemble methods like ANKF, ETKF, and other versions like that. Okay, now I'll keep this slide short, the presentation of it, because most of it is tedious. Somehow you can repeat the same procedure and use these ideas from adaptive particle filtering to do tempering and MCMC moves when you move from pi hat n minus 1 to pi hat n. All right? And all right, there will be some different weights here, but to an extent these are details, and there will be a different invariance distribution that your MCMC steps would need. But one thing that is very neat here is that once you do this break in the correlation in time, your update so that you have good MCMC mixing need only be on a fixed size interval. So n, n minus 1, n minus 2, n minus L. This is all the states you need to update, right? And L could be fairly small, right? It could be 1, it could be, even you could update less. All right, so I mentioned this thing about principles, so we would like to actually also prove something about this. And to a way, we would like to extend this old paper by Alex, Dan, and AJ in a dynamic context. So I copied the equation from the paper. I'll try to talk through it. So what we can do is we can actually stabilize, if you want, some mean squared error. When we look at the filter, which is the object of interest here, so this is the density of xn given all the data up to time yn. And this, if you want, the particle approximation of it, and phi is some test function. Now, there are some assumptions that we will use. We will assume that all coordinates in my x are, if you want, spatially independent, except little m of them that are correlated. All right, so how does this work? I assume that have a fixed m that could be quite large, but smaller than d, but there is correlation between these coordinates. And then when I take d to go large, somehow the rest of the coordinates will be independent, right? So this is, if you want the assumption, this will be an assumption that we'll use for the transition test, the likelihood function, and these approximations that I'm using. And perhaps to an extent, this is, if you want, a strong assumption for application, but somehow it was the most general we can come up with. So there are two parts in the error. The first is the Monte Carlo error when we're tracking the pi hats, and then there's the bias. So this bias term comes from not using, if you want, the right mu function that we use to break this correlation, and somehow we require slightly assumptions on bounding strongly f and g below and above. And somehow this, if you want, the Monte Carlo bound that you get when you track pi hat. Now, I copied the expression from the paper, and just to make sure that something is clear here, is that, all right, so for these constants here, somehow, this is the error term, and the smaller, the bigger you make L, the less is the bias. But of course, there's a compromise that, for practical reasons, you are forced to use L smaller. So if I make L very large, this term disappears, right? And also, if I choose these guys to be close here, this term stays low. Now, for this term, somehow there's this little n constant that might imply that this is not a time uniform bound, but in fact, this is a constant that has to do with the effect of the MCMC steps you're using at every time n. All right, so with some additional strong assumptions on the problem, the state space, and the actual MCMC kernels you're using, you can actually work this to be also, if you want, time uniform. All right, so yeah, I'm almost finished. So yeah, I think the good news here is that somehow you get some stable error in dimension, all right, with some assumptions. All right, so this is the, and for the first part, which is this one, essentially the work is a elaborate or not so elaborate extension of previous works by Dan, Edge, and Alex. And the second one is fairly standard in the world of filtering and actually bounding things for partial filters. All right, so some numerical results. We've tested this in a few models, and we were quite surprised by how well it did. So we tried an linear Gaussian example, a Lorentz 96 example. Just for the sake of an aesthetics, I will show it with the example from a PD. So we'll use the shallow water equation with additive noise for the dynamics. So we run the PDE, add some noise in the coordinates, and then observe different quantities in the lattice, right? So we observe the height everywhere, and in some, if you want, coordinates, we observe also the two velocities of the water, and this is our initial condition. Somehow we have a very large peak for the water, and then it will ripple out, right? So maybe this is not tsunami size, but somehow it has some interesting dynamics. And we compared with some ensemble Kalman methods. Somehow the whole point to say this picture is as time moves ahead, somehow we can get better accuracy at the expense of a much larger computational cost. So there are some accuracy plots here that somehow go and look. So this is, if you want, for the height, I think, and looks in time at the error. So somehow the scale is a little bit shows the difference, and somehow this is, if you want, some tracking in the first moment, and actually in second moments, at higher order moments, things were actually even better. So there is good performance, and somehow the main message of this talk to conclude is, all right, at least when we speak for partial filtering, there has been some literature on how to localize in space and how to localize the weights and the resampling, and somehow, to an extent, there is some understanding there. The point here is that localizing in time can also help, and somehow you get an algorithm that can be stable, probably stable in time. So just some references. So this is fairly old work, and this is what I presented in this fairly recent paper. So thanks a lot.
Are there comments or questions?
So this n here is just theoretical assumption. Right, so for the actual implementation is irrelevant. It's just to get somehow, it's just essentially what we need is we need the change of measure with something that is spatially IIT. And we don't want to get any singularity there, right? So we just, it's an absolute continuity kind of requirement essentially. For the L, right, this is a good question. So for the little L, you don't need to worry much because the temperatures are selected automatically. But for the big L, which is if you want this constant here, somehow it's a matter of, you know, how good your MCM systems are. The more you can do, the better, but the computational cost can be very large. So to give you an idea, the run I gave you here, somehow it needs a few hours, right? If you need to do some multiple runs, you will need weeks, right? Or a week. To do 50 runs, we needed a week or more of computing time. So L here we use something like 2 or 3, sometimes 1, sometimes 0. But something small.
So if you're interested only in the last value or some of the last values, then it's even more relevant to truncate this time dependence.
Yeah, I mean, the time dependence, the point here is that when you do this truncation, you add a bias. And in practice, you do not know what it will be. If you put assumptions, you can show at least it will be stable in the dimensions, but there needs to be some proper, if you want, more sensitivity type analysis on, you know, how capital L affects the bias and, you know, there you need to do more if you want work than what I'm showing here. But it can work also with small numbers of L. So the results we saw were good, and to be honest, we're actually surprised that the results were as good. So this was the kind of thing.
Does it require to be smart for the choice of mu of this?
So for mu, we try to choose if you want. So I'm writing this here. I know it's not. I'm not very good with. So we try to choose. Maybe here is the correct place. Something like this. So this is the predictor at time n minus L plus 1. And for this, we used NENKF or ETKF, and we got from that a parametric approximation for a Gaussian. From the Gaussian distribution you get from that. So there's a parametric approximation there, which is easy to do, but it means that you use something else.
A couple of questions, very simple questions. So you said that by linking the angle and it also showed that the prison we have is quite good compared to what we have in the progress. So you say that the bias of small it's not an impact. And the second question I have is saying, okay, comparatively much more accurate, 6 inches the others. Yeah, I mean, I'm interested if you have any idea how to pick up. You know, so that is helping the time of transition is helping, probably the results of your transition. Space. Do you have any other things that make it?
Let me answer the last one. Right? So I'll just go back to the basic version of the algorithm without the tempering, because the tempering is a mess, right? So somehow this step, this computation is embarrassingly parallelizable, right? So this you can parallelize. The addition and normalizing is not fully parallelizable, but can be done scaled nicely. This thing is more difficult, there is something. There are some ways out of it. And also there are some ways where, especially if you have models like this, people localize and do parallel particle filters and add an extra particle. So there are ways to parallelize the algorithm. And you will get some speed up that could be from a factor that is roughly proportional, maybe not quite there, as the number of workers you put in the parallelizers. Right? So this is one way to accelerate the computation. Now for
example, you need to wait for all the particles to be finished, and then need to actually also depending the dimension, read all the particles with the weight.
yes,
They're not completely dependent, that's the problem.
If they are something, if you use something like here, which is essentially something from one application, somehow there are approximate versions where you could sort of parallelize and perhaps you want to also keep some part of it parallelized. It's not, but it's not what I said. But there are some solutions that if you're happy to accept the bias, you could also parallelize the result, even without remaining localization. So there are some parallelization with something like this. Stuff that is much more complicated. Some of them start to become more.
So you don't care about the bias and how big the bias is.
Yeah, I mean.
Affect the accuracy.
Yeah, so this is also a good question. So if you go, if I understand what you're saying correctly, is which step here, if you do wrong, will cause more bias, right? So usually the errors comes from here, right? This is the problem where the errors come from. And somehow, if you do a better sampling algorithm that is, has better properties, you will get very much improvement. But with the parallelized versions, it's almost indistinguishable. And this is all tested in small dimensional problems, right? Yeah, I understand if people are a bit worried about this, but in terms of parallelization, there's a lot of work that is still, ready to be exploited, and it would be interesting to know, to give you a nice number. So if I had it, even a 2 example, I would be happy, but I'm optimistic. This I can say. Now, on top of this, for data simulation problem, you can also use localization space ideas, which explosion and bigger parallels. So there is potential for scaling this, but there will be a lot of work in, the method, understanding more what we're doing, and also the engineering side of things, which is, these algorithms are complicated and somehow need some time for people to get used to their implementation. And for the bias, yeah, I mean, somehow there are 2 aspects. One is the aspect, to get a result like this, where we make assumptions, and some of them are realistic, some of them maybe not. But in the actual empirical things we saw, and especially in like Gaussian space models, we know what the answer is. Somehow the performance was much better. It's just that we put many more hours into the computation than the standard ensemble type ideas or ensemble traffic. Right? So if you have the extra computation, use it. But if you don't.
Okay. Let us thank all the speakers this afternoon.
So there should be wine and drinks.
I see the wine and the drinks.
Yeah. Behind us, or maybe it needs a few minutes more setting. We can move over there and continue discussions.
You should say that tomorrow we will not be here.
Yes. Tomorrow we will be in the Ditchburn Lecture Theatre, which is in the J.J. Thompson building, which is kind of across the road from this location. So you had those who were part of the program, they know where this is. But, so you follow the road in front of the top here, and then the building you end up you face if you had that direction. It's J.J. Thompson. In there's a lecture theatre called Ditchburn.
Should we take our lunches?
Sorry?
Should we take our lunches?